Okay, so we have conquered the harmonic oscillator, and we will use that for sure as a great system to analyze with spectroscopy. Another sort of thing we want to get under our belt is to handle a two-level system. You can imagine a two-level system as being any two levels of whatever you want. Okay, that could be two of the harmonic oscillator levels. It could be two electronic energy levels. It could be a combination of electronic and vibrational degrees of freedom. But we're going to focus our attention on two because two is the minimum that you need to see some sort of spectroscopy usually. Okay, and so what we're going to do is right now I'm just going to sketch out the plan, and then there'll be another section of this lecture segment where we go over a program that will let us calculate the time-dependent quantum mechanical dynamics with a two-level system for an arbitrary field that couples the two states. Right? So let's call this the ground state and the excited state. And we've sort of looked at this before, of course. So the Hamiltonian, we will break into two parts. One will be what we might call the H-naught Hamiltonian, the field free, the states that you have with no coupling. So we'll call that H-naught. And then we'll have some coupling term that I'll call V that connects the two levels together, right? And when we write these down in the basis, this will look like the energy of the ground state times G plus the energy of the excited state with the E, excited state projector. And then we'll have the coupling term, so plus G, we'll call it VG, E, and E, plus the complex conjugate. The Hamiltonian has to be Hermitian. All right, VEG, G. And of course, this VG and VEG, they can be real, and they can be complex, real, whatever you want. They do have these two have to be the complex conjugates of each other. We worked out already the Rabi oscillations with this problem, which was assuming that we started in the ground state, then we have the field, turn it on, we don't think about the turning on part, and then we see how the probability changes for being in the excited state as a function of time. Now, of course, once you have the field on, the eigenstates change. So in some sense, kind of is weird to ask, well, why would we be asking this question about a state that's not an eigenstate of the Hamiltonian? Well, one way to think about it is the states that you can exist in a quantum problem are not only the eigenstates of the Hamiltonian. That's just a basis, all right? And so because it's just a basis, it means that we don't always need to be hemmed in by only being in a one energy eigenstate or the other energy eigenstate, right? For a system to evolve, if it's oscillating, for example, it's not in just one of the energy eigenstates of the, say, harmonic oscillator Hamiltonian. Otherwise, it wouldn't oscillate. It would be a stationary state. All right, so there's two regimes of the change that we want to consider, and these are actually very important. So what we're going to do is we're going to imagine that VGE is time dependent, right? This problem is really only interesting, I think, when the potential changes in time. If it doesn't change in time, we just have the Rabi oscillation thing like we had before. So there's a lot of different ways it can change in time, and that's how we're going to kind of deal with this in the class. One way that it could depend on time, for example, is it could be oscillatory, like sinusoidal. Right? So it could have itself a frequency, a resonance frequency. And what we anticipate is that when the frequency of the field matches the frequency of the energy gap, we're going to have a huge energy transfer, for example, a very large probability of going from the ground state to the excited state. Okay. So it could be sinusoidal. It could be constant, in quotes. What does it mean to be a time-dependent and also constant? What I mean by that is, if you were to decompose it into its frequency components, you wouldn't see high frequencies. So if we do a little sketch for sinusoidal, it might look something like this. And a sketch for constant might look something more like this, where this is time, and this is the magnitude of VGE. We see there was a time in the past when it was off, and then we turn it on, and it stays on. We could also wait for it to turn off again. all right? And so there's a couple different regimes here which are very interesting, and then we can treat all of these or consider all of these explicitly, meaning we can just solve the Schrodinger equation for the two-level system with an arbitrary coupling field. And there's a very simple MATLAB program that will do that, and I'm going to set it up first, and then we'll work through the code afterwards. But I want to call your attention to two sort of regimes of the change, right? And one regime of the change that turns out to be important also for chemistry, not for spectroscopy, and that is the rate at which we change this coupling field, right? So one limit would be that we turn it on very fast. And what would very fast mean? Very fast, infinitely fast, would be like what we did with the Rabi oscillations, right? We have nothing, and then we turn it on, and then we keep it on. So we might say that the field turns on at 0, it was off all the way from negative infinity to 0, and then poof, it comes on. It's some fixed value, and then it stays on as a function of time. Okay. Another option is the sort of alternate limit of this, is that in the past it was off, but then it comes on super, super, super slow. It might very well still arrive at the same, if we call that 0 or whatever, it might very well end up at the same value, right? But you're turning it on more slowly. And you might think, what difference does it make how fast I turn it on? All right, so the punchline of this is it matters. And it's going to matter in some sense by thinking of the frequency content that's in this field by itself. Right? So if I have a field that turns on abruptly, that field that turns on abruptly is going to actually have very high frequency components in it, even though there's nothing oscillatory. And that's because if you think about taking this function and constructing it from a sequence, a sum of sines and cosines, you're going to need a very high frequency component, many different high frequency components to achieve this very fast turning on, right? Another way of thinking about it, what would this sound like? It would sound a little bit like a click. And a click is a very sharp sound. When you do the Fourier transform of a click, you'll see that it has a broad spectral content. Whereas here, we have a very slowly varying function. So you can almost, even in your mind, imagine, I see how to approximate this function. I'll just get one sine wave. Now I know it's going to come back down again. So I might need to add a few sine waves together to cancel this out. But this part of the rise might come from a single low frequency component. All right, so all of this is, of course, the elephant in the room is that you can understand all of these things through Fourier transforms. And we will absolutely do that. That'll especially be important when we look at time-dependent perturbation theory. Here we're not doing perturbation theory, we're doing it exactly. So I want you to see it exactly, and then we'll look at what happens when we do it with perturbation theory. Okay, so here's the one way to think about a very quick change in a Hamiltonian. So if you imagine, for example, having a particle in a box and taking this as your state. So we're just going to assume that our system has been prepared in the ground state. So at t equals 0, the system is in the ground state, n equals 1, and this is what it is. And then what we're going to do is we're going to imagine that we extend the length of the box a little tiny bit. All right, so we make it a little bit bigger. Let's call that epsilon bigger. So we have L goes to L plus epsilon. Okay? If we make this extremely small, and I picked epsilon not because it's because in math it's often used to indicate an extremely small number. If it's extremely small, arbitrarily, infinitesimally small, then of course the length of the new box is not going to be very different from the length of the old box, right? And so that will mean that our wave function will be almost like the wave function that we started with, plus maybe a tiny little bit because the box got a little bit longer, okay? But nevertheless, our new wave function, the one with a slightly bigger box, is going to look very similar to the one that we started with. All right, so if we started in n equals 1, for a particle in the box, with a wave function like this, our new one that we have with a slightly bigger box is going to be very, very similar. So effectively, n equals 1 only, meaning, of course, the wave function will be some superposition of all the wave functions, of all the eigenfunctions. So let's call that C of k, phi of k. And where k is equal, I guess I'm using k in place of n. How about I switch it to n, since I've already started using n. We'll start again. Grr. It's fun when you make it up the top of your head. All right, so the wave function to start with, right, I guess I can call it in time, is going to be the sum on n, c of n, phi n, where the phi n's are just the particle in the box eigenfunctions, or eigenvectors, right? We now know how to go between the two of them. And the idea, and it's not proved here, I'm just giving you the rough idea, and you can, of course, prove all this. If you make the box infinitely smaller, infinitesimally smaller, then what's going to happen is basically the new wave function is going to look just like the old one, but it's going to be a little bit longer, and it's going to stay largely in the ground state, which is to say that basically Cn is going to be approximately 1, and all the other ones, Cn equals 1, I mean, is going to be approximately 1, and all the others will basically be 0. Now imagine I do this again. And you get the point. I do it again and again and again and again and again, and what's going to happen is I can gradually open the size of the box, make the box bigger, and as I do it, so here we now zoom fast forward, many epsilons later, right? So now we have done n epsilons. At each time, so if we remind ourselves the size of the box, we started here. Each time we make it bigger, the wave function is going to basically track and get a little bit bigger each time that we make the box a little bit bigger. So eventually, it'll look like this. Right? And it will still be the ground state of the new, larger particle in the box. All right. So this kind of transformation, where you go very slowly, is called an adiabatic transformation. And we're doing it very, very slowly. As you, in this case, the term adiabatic refers to the fact that the state doesn't change. Right? So the state stays, the state doesn't change. Of course, you're probably used to hearing adiabatic discussed in thermodynamics, which is to say that you do a process with no heat flow, which is also good. Another way, so maybe you could think about that. I mean, of course, you can do a process adiabatically, but also irreversibly. You can just jam down really fast on your bicycle pump. That'll be adiabatic because there's no time for the heat to flow, but it's certainly not done in a reversible way. So don't think about it because it's done in the slow way. Think of it because essentially I've stayed in the ground state. So if you want to think, does the, would there heat flow? I mean, of course, we're at 0 temperature, so talking about heat flowing is kind of stupid. But, we're staying in the ground state. What's happening to the energy of the ground state? The energy of the ground state, which is a function of L, is actually going down. Right? So as we expand this piston, obviously it's proportional to L squared. It's going to go from L squared to L plus n times epsilon squared. And that energy is going to go down. So if we were to track the new length, the energy of this, it'll go, as we make this, it'll get smaller and smaller, like L squared. All right, so in some sense, what we're doing is, of course, we're expanding up essentially what is a one-dimensional piston, right? It's a linear piston. You can think of it like a syringe, like a super small gas-tight syringe, but even smaller, so there's no two-dimensional extent whatsoever. And as we make this one-dimensional piston larger, we do it gradually enough, right? We could still do it quickly, but we're doing it gradually, a little tiny bit at a time. The system stays in the ground state. All right, so that's the adiabatic limit. The next limit that we're going to consider is when you do it abruptly. All right, so imagine I take the same particle in the box system, where now we go from the initial state, which is this one, to the final state, which is that one, but we do it out in one step. Well, if we do it in one step, we have no choice. The state of the system is this. So this is the, if I draw the wave function, it looks like this. Right, that might look like a kind of goofy wave function, but it's not actually as goofy as you think. What it really means is that I have a wave packet that's isolated or that's localized more on one side of the box than on the other side of the box. We know what's going to happen if you do this. This is obviously not a stationary state. So we're going to have a superposition of all of these, of many of the eigenfunctions of the larger box. Okay, so we can calculate then, we can call that t greater than 0, for example, right after we make this change. So it's like t naught. T naught might be this one that we started with. And we just need to figure out what are these expansion coefficients. But we know how to do that because it's just the scalar product of this function with each of the new particle in the box wave functions for the bigger box. All right, and those are going to be non-zero. And so what's going to end up happening is you're going to have lots of amplitude in eigenfunctions of higher values of n than 1. Right? So this thing will evolve in sort of that complicated, very anharmonic way that we've seen in our demos looking at particle in the box wave functions. We started out with an example where you could put a particle in the box, make a ramp, localize the wave function on one side, and then remove the ramp. This is exactly this example that I just showed you. Because now we start out with the ramp ground state, but the ramp ground state's not an eigenstate of the no ramp Hamiltonian, and so this whole thing starts, oscillating in this sort of very haphazard way because, of course, the particle in the box is super duper anharmonic. All right, so that's an example of what we now call in the jargon the sudden approximation. Right. The convenience of these two things is that we know essentially what happens from each of them by not having to really do a whole lot of work. Right here, we just have to figure out what's the new system, where we know from our logical argument that the system is going to stay in the ground state. So as long as we know how to calculate the ground state, we're done. Here, we might not know everything, but we do know that we will have to still figure out how it evolves as a function of time. Here it won't, because it'll stay in an eigenstate of the Hamiltonian the whole time. Here it'll evolve later on. But what we really need to know how to do is calculate these overlap integrals, if you want to call it something the way chemists might call it. But these scalar products between our target function, which is this initial wave function, each of the basis functions of the new Hamiltonian. All right, so what we're going to do is we're going to check all this out, but using a two-level system and make sure that this works when we calculate everything dynamically exactly.